we are going to solve a new Leet Code problem, that is binary search tree to greater sum tree. Now in this problem we have been given a binary search tree. Now we will convert this tree into a tree whose node will be replaced by all the nodes that is greater than the current node and the node itself. Let's understand the problem. Let's say for this 7, so what are the nodes that are greater than 7? That is 8, right? So 8 plus this current value, that is 15. Those, so 7 will be replaced by 15. For example, this node 8. Are there any nodes that is greater than 8? No, right? There aren't any node. It is the rightmost node. So it will be replaced by 8, the current node itself, plus 0. Because if there aren't any nodes, so let's consider this as 0. For example, this 6. What are the nodes that are greater than 6? That is 7 and 8. There are two nodes which is greater than 6. So 7 plus 8, that is 15. 15 plus 6, that is equal to 21. For example, let's say consider about this 5. So what are the nodes that are greater than 5? So there are three nodes, 6, 7 and 8. Summation of these three is 21. 21 plus 5 is 26. This is it. Now let's consider for the node 2. What are the nodes that are greater than 2? There are 3 is greater than 2, 4 is greater than 2, 6 is greater than 2, this one greater than 2, this one and this one. So 1, 2, 3, 4, 5, 6. There are 6 nodes that are greater than 2. So summation of all these 6 nodes will yield 33 plus this node, that is 35. So this is what the problem is. Now, when you at first see this problem, the most trivial solution that can come to your head, since it is a binary search tree, we know the in-order traversal of a binary search tree produces an array of all the values in ascending order. Now, if you do in-order traversal on this binary search tree, so it will look like this. That is 0, 1, 2, 3, 4, 5, 6, 7, 8. That is, the values are present in the ascending order of their values. So we know the left. Now, if we calculate the prefix sum on this array, so it will also look like this, right? Now we know the farthest farthest node on this binary search tree will be of maximum, right? That is 8. 8 is the maximum value present here. And the first node of this binary in order traversal of binary search tree will be the least. That is 0 is the least. So 0 is the firstmost one. So if we make a prefix sum of this entire array, now for this 8, right? For this 8, if we want to know the value of this 8 will be, if we do just 36 minus 28, that is 36 minus 28 is 36 minus 28 is 8, right? This one and this one. So if this is a prefix sum technique, for those who have solved the prefix sum already, we already know, if we want to make, let's say we want to calculate a prefix sum of a some random, let's say some random array. Let's say the prefix sum has come like this, something 23, let's say 1, 3, 6, 10, 15 and 21, right? So if we want to know the summation between these two elements, what we do is 21 summation of these two elements, that is 11, right? So what to do, we use 21 minus 10, that is 11, right? So if we do 21 minus 10, it will be 11. So 5 plus 6 is the 11. So this is the answer. Now if you want to know the summation of this element, so what we do, we use 21 minus 15, that gives 6. That is how we use prefix sum technique to find the summation of a particular sub array, or let's say sub part, right? So for this 8, if we do 36 minus 28, because I want to know the value present at here, so 36 minus 28 will equal to 28, and 8 will be this answer. Now let's say for this 0th part, if we want to know the what will be the answer for this, if we do 36, for example, if the index is 0, we don't need to do I minus 1. So index is 0, the enter yield, because the first portion will, the summation of all the nodes will be replaced by this one, so it will be the total array summation. So this is 36. So let's say for the fourth, let's say you want to calculate what will be the value for this fourth part, right? So what to do? Just do 36, the total, minus 6. That is 36 minus 6, that is 30. Now for at this 4, let's say you want to calculate for the fourth index. So what will do, you will subtract the maximum, that is maximum you can get 36, minus one minimum, one, just one ahead of it, one previous, though that is 6. That is 36 minus 6, this is 30. So 4 will be replaced by 30, and this is, if you do these things for every node, you can easily figure out what will be their value. So this is how to do, this is the first technique what you can apply. So i have I have prepared something for you. This is how the first code will look like. We will just calculate the prefix sum of the entire array. After you just do an in order traversal, push all the nodes into a array, just calculate the after this, just calculate the prefix sum, and with that prefix sum just find out the what will be the value. This is the first approach, but it is a costly approach, don't you think? Because we are traversing this tree multiple times. First of all, you have to do the in-order traversal to understand what are the nodes. Then have to calculate the prefix sum. Then you need to construct the tree. This is order of n solution, but it's a, there are a lot of traversals are needed, so it's a bit expensive. Can you do better than that? Yes, we can do better than that. There is second approach available. So what to do? Have you noticed one thing? We are getting at the rightmost part. For example, we are starting our operation from the rightmost corner. Okay. First of all, calculate this. Then 8 plus 7, 15. Now try to know what is the left sub array. No, there aren't any left sub array. So return 8 plus 7, 15 to this node. So 15 plus 16 is 21. Now just try to know whether there is a left sub array, left sub part. There is a left tree, that is 5. Now return this 21 to 5, to 21 plus 5, 26. Now return this 26 to this node. Now the summation of the entire subtree is calculated, that is 26. Return this to 4, that is 26 plus 30. Now return this 30 to this to its predecessor, that is 3, that is 30 plus 3 is 33, right? This is how to do it. So how can you do it? Just use a simple DFS approach, simple depth first approach, where we'll where we'll reach the top rightmost portion at the beginning, and from there I will start building things up. So what to do? Let's code this up. Let's maintain a sum variable, because we want to know the current sum, that is the current sum that has been calculated so far. So let's just use a simple DFS approach, right? So what we will do, we will first of all reach the rightmost corner, right? Because from the rightmost part of the tree our calculation will begin. So right, so what to do? Just calculate the sum, because the sum will be, we have reached 8, right? So the sum will be, sum was 0, so 0 plus 8, that is 8, right? Now you will update root dot value equals to this sum. Now I have traversed right, so I need to traverse the left as well, right? So just do a left. Now this call will, the sum will be 8. Now I will return to this place. So I have already calculated the right of it. So here will be sum was 8 from the previous portion. 8 plus 7, that is sum plus root dot value, that is 8 plus 7, 15. Now root dot value equals to 15. Now I will traverse the left, but there aren't any left. Now sum is updated to 15. Now for this part, that is dfs dot root dot writer was calculated earlier. Now we will execute this part, that is sum was 15 from the earlier portion. Now the root sum, that is 15 plus root dot val, that is 6, that is 15 plus 6, 21. Now update this root dot val with the sum, that is 21. Now go to the left. This is how the entire tree will be calculated, and I will update the value with the sum updated sum value each time. So just do it. Just do it. Let's first run. I did end up creating some problem. So what it is, why it's saying, oh sorry, I forgot to pass out the base condition. This is very bad, because if the root equals to null, I just return it now. Because if I am here, if I again do root dot write, it will be null, right? If I do root dot null dot value, it will give a null pointer exception. So this is a must condition. The terminating condition is must. This is it. The base is passed. And the time complexity of this approach is order of n. And the space complexity, it will take some kind of space, because the recursion takes some kind of call stack to compute the recursive calls. So the space complexity will be order of h, that is order of log n, because the height, because the maximum function calls that will be pushed into the stack will be order of height, right? Because you cannot call more than the order of each time. So the maximum function calls that can be stored in the call stack will be order of h, that is order of log n. So this is what it is. It is the most optimal approach for this problem. I have already calculated this. I am attaching this as my code. So this is how it is. It was a bit interesting, but it is an easy problem if you have carefully solved a lot of BST problems. So that's it for me. Thank you.